Mike's talk today is actually the third talk in a series of 4 on the fundamentals of Apache Kafka. Today's session will cover all the technical details you need to know to understand how Apache Kafka works. This series as a whole is designed to give you actionable insights, whether you're just getting started or have already built stream processing applications. Today's session will be about 60 minutes long, and we do have our Kafka experts on the line to answer questions as they come in. So please submit your questions using the Q&A panel at any time throughout the talk, and the team will address them as soon as they can. This talk will also be recorded, and we will send you the slides and recording via email later today. So with that, I'll hand things off to Mike.
Thanks very much, Jason, and welcome everybody. Thank you all very much for joining us in the continuation of our series on Kafka fundamentals. So this is our third session in our series, and here we're going to explore some of the important concepts covered in our previous talk in more detail and build a deeper understanding of how Kafka works. As Jason mentioned, if you have questions, please ask in the chat as we go. I'm joined by several fantastic teammates who will be answering questions as we go through this session. So here's a summary of what we'll be covering today. First off, we'll take a high-level look at the programming logic for a Kafka producer and consumer, with some examples in Java and C#. We'll explore how replication works in Kafka and learn more about how it provides high availability and durability for our data. We'll discuss different options for data retention, take a closer look at how producer and consumer groups work under the covers, the different types of message delivery and processing guarantees supported by Kafka, including an overview of exactly once semantics, or EOS as we call it, a brief discussion of options for monitoring and troubleshooting in a Kafka environment, and then finally, we'll wrap up by looking at some of the different options Kafka provides for securing the cluster and our client applications. So to start out, let's take a look at a code example for a simple producer application written in Java, which is the native client that ships with Apache Kafka. It's not important to understand all the details of this code. Here we're going to focus on the high-level structure of a producer-client implementation. So when looking at a basic producer application in Java, there are 4 main parts to highlight here. First, we start with the configuration section where we define various settings. Some of these are required, some of them are optional for our producer. And these configuration properties are important for kind of specifying how the producer-client library will perform and operate internally. And we're going to take a closer look later in this session at some of the inner workings of the producer-client library to kind of understand what's happening there a little bit better. We then construct a producer object using these configuration values. This particular producer is configured to send string keys and string values in its messages. We then define some code to be executed before the application terminates to ensure that we close the producer resources gracefully and end our application in a consistent deterministic state. This is actually important for any type of Kafka client, whether it's producer or consumer or Kafka streams. We always want to properly close and release resources before shutdown if possible. And then finally, we see the main part of our implementation, which contains logic for actually sending data to our Kafka topics. A single producer can send data to 1 or more topics. In this case, we're just sending to 1 topic whose name is Hello World topic. So as you can see at a high level, looking at this code, the API for producing data to Kafka is actually quite simple. Most of the complexity of actually integrating with Kafka and handling communication with the cluster is handled internally by the client library. That's where most of the heavy lifting is actually happening. And then one more note that while Java is the default client with Kafka and is a common choice, it's not your only option for building client applications which integrate with Kafka. Kafka defines a language-independent binary protocol that can be supported by any programming language, and there are native client implementations for most of the popular programming languages in use today. Confluence supports several of these, including a high-performance C++ client called Liberty Kafka, and several other language clients that built on top of that, including .NET C#-based client, which we're going to see an example of on the next slide, Python, and Go. So now let's look at a code example of a consumer application, this time using C# instead of Java. Again, the focus here is not on the details of the code, but rather on the high-level structure of the implementation. So in this first highlighted section, we define, again, our required and optional configuration settings for our consumer client, and then we construct the consumer with these settings. In this example, the consumer is configured to read messages with string keys and string values, just like we saw with the producer on the previous slide. Next, we define some callbacks to process messages when data is received, as well as callbacks for handling any kind of failures that might occur. Then we subscribe to the topic or topics that we want to consume from. In this case, we're just consuming from one topic called Hello World topic, the same one we saw on the producer side on the previous slide. And then finally, we have a loop that polls continuously for new data from Kafka. As the data is received, the callbacks defined above will be invoked to handle new messages or any failures that occur. And we're also doing resource cleanup here in this code as well. That's kind of implicit in that using line of code on line 20 right there, but it is happening here as well. It's always important to clean up before you shut down the application, so it is happening here as well. It is important to note that Kafka consumers poll for new data. Some messaging systems are push-based, but Kafka is pull-based. In general, that tends to provide a higher level of decoupling between components, and Kafka has kind of chosen that architectural approach. And overall, communication between clients, whether it's producer or consumer, whatever, and the Kafka cluster is always initiated by the clients themselves. Producers push data to Kafka, consumers poll for data. Okay, so when you create a topic in Kafka, you define a number of partitions for that topic, which impact scalability, as well as a replication factor, which impacts the availability and durability of your data. So here in these next couple of slides, we're going to take a closer look at the replication component of Kafka, which is very important, of course. And replication occurs at the partition level in Kafka, so individual partitions are replicated to other brokers for high availability and increased durability. So in this example, we have a single topic named topic 1, and it has 4 partitions, numbered 1 through 4, and each partition is replicated 3 times. So we have a replication factor of 3 defined for this topic. By the way, a replication factor of 3 is a pretty common number for many production environments with Kafka. It's a pretty good balance between high availability, having multiple copies of your data in different brokers, while at the same time not requiring excessive storage and I/O costs maintaining those extra copies of the data. Of course, that's a configurable setting, and you can go higher or lower as your preferences might dictate. But if you've worked with other distributed data systems before, like Hadoop or Elasticsearch, things like that, you're probably familiar with that concept of replication factor, and specifically a replication factor of 3 as being kind of a pretty common choice in that area. Okay. So in this example, each partition with a replication factor of 3 has a single leader and 2 followers. Okay. So these are the roles that a replica can have in Kafka, and for every partition there's 1 leader and 0 or more followers. So Kafka clients, such as your producers and consumers, only access the leader of each partition. Followers, in turn, poll the leader periodically for new data and then write it to their own local commit logs to create that redundant copy to give us that high availability. So in this model, leaders have more work to do than followers. Leaders have to handle all the incoming requests from producers and consumers, as well as distributing their data downstream to the followers that are replicating that data. Whereas the followers have a much simpler job of simply just consuming from the leader. And by the way, followers are polling for data for the leader, much like consumers poll for data. It's kind of like an example of internal consumption that's happening within the cluster. Okay. So Kafka does its best at the time you create the topic to distribute the replicas for your topic evenly and equally across the different brokers in your cluster, as well as also distributing the leadership for those partitions equally. Since leaders have more work to do than followers, we don't want to have a situation where a broker has only leader replicas or only follower replicas. That would potentially result in an imbalance in workload and hotspots within your cluster architecture. So Kafka does a pretty good job of distributing the replicas and the leadership for these partitions equally across the cluster. That way, producers and consumers will be accessing all the brokers in the cluster, just not for the same partition, but for different partitions they might be interacting with. One other note is that there is work ongoing right now in Kafka to make it possible to actually read from follower replicas instead of just the leader. And if you're curious about that, there's a KIP, or Kafka Improvement Proposal number 392, that kind of describes that in a bit more detail. Currently, replication is only about providing high availability and durability, but in the future, having multiple replicas could also provide some performance advantages by distributing read operations against certain partitions and supporting greater data locality. And because Kafka tends to be a fairly read-heavy system, that could provide a lot of benefits. So stay tuned for more in that particular feature. But as of right now, today, all access to each partition happens on the leader only. Oops, sorry about that. So within a Kafka cluster, one of the brokers has a special role called the controller. And any broker can act as the controller, but only one will be active at any given point in time. And one of the important functions of this controller broker is to monitor the health of all the other brokers in the cluster via Zookeeper, and if a failure is detected, to reassign partition leadership as needed. In other words, provide automatic fault tolerance for your cluster. So here we have an example that kind of shows what happens if a broker fails. In this example, broker 4 has failed. So the controller will detect that failure by monitoring state in Zookeeper, and will then reassign partition leadership for topic 1, partition 4, to one of the remaining in-sync replicas for that partition on other brokers. In this case, it's selected broker 2 to become the new leader in this particular case. By the way, an in-sync replica is one that's keeping up with the leader when replicating messages, and an in-sync replica in Kafka, or an ISR replica, is guaranteed to have all the committed messages that the leader has. In other words, it's strongly consistent with the leader. Okay? And a committed message is one that is visible to consumers. So essentially, an in-sync replica will have all the same messages that are visible to a consumer that the leader has. An out-of-sync replica, one that's not keeping up, may or may not have all of those messages. So we don't typically want to rely on an out-of-sync replica for recovery in these kind of failover conditions. So all partitions that had replicas on broker 4 will now be under-replicated. And Kafka, by the way, does not automatically replace lost replicas. This may be different than other distributed systems that you might be familiar with, where replacing lost replicas happens automatically. Kafka tends to take a more optimistic approach to its design, in assuming that if a broker goes down, more than likely it's probably coming back soon. In that case, we don't want to incur the cost of copying a bunch of data around the cluster to replace those replicas if it's really not going to be necessary. So if there is a situation where a broker goes down and it's for an extended period of time, there are ways to manually create replacement records in replacement replicas in Kafka, but that doesn't happen automatically. So when broker 4 goes down, all of those replicas that you see there, topic 1 partition 2, topic 1 partition 3, topic 1 partition 4, will all become, those partitions will all become under-replicated until that broker comes back or until you take some manual action. And if we don't have any in-sync replicas to fail over to when a broker fails, then producers will not be able to write to that partition anymore, and consumers will not be able to read from that partition. In other words, the partition will be offline or unavailable. Of course, one of the reasons you want to have replication is to be able to have additional copies of the data to fail over to in the event that something like this happens. So clients, such as producers and consumers, will be notified whenever the leaders change. So producers and consumers will receive updated metadata from the Kafka cluster telling them, in this case, that topic 1, partition 4, is now on broker 2 in terms of leadership, and that's where they need to access that partition. So basically what happens is when these kind of failures occur is that the clients themselves will fail, but through automatic internal retry logic, the clients will refresh metadata about the cluster and will discover there's been any leader changes and will automatically retry to connect to the newly assigned leader for the given partition or partitions. And all that happens automatically and transparently to the client application in most cases. One final point to mention around replication is we mentioned the importance of replication for high availability, ensuring that we can always access our data for read and write. And of course, that's the obvious and very important benefit that this feature provides. But it's also about durability as well, increasing the durability of your data. And just to provide a little bit on that, it's important to note that when new data comes into the Kafka cluster from the producer and the broker writes that data to the file system, that data may not actually go to disk right away. It may actually be buffered in the operating system's page cache temporarily before eventually being flushed to disk. And in the Kafka world, Kafka may commit a message as soon as it writes to the OS or to the page cache or the file system cache before the data actually gets synced to disk. So having replication is also increasing our durability in the unlikely event that a broker gets a message, it writes to the file system and it gets buffered by the OS, and then the broker acknowledges success for that message and then immediately crashes before it has an opportunity to sync that data to disk. Without replication, that could result in data loss. So having replication allows us to ensure that we don't lose data in those kind of very rare, unlikely scenarios like that. So replication kind of has two benefits. It's high availability, the obvious benefit, and durability, maybe the more subtle benefit there as well. So very important to have this, especially in production environments. All right, so now let's take a little bit deeper look at data retention in Kafka. So one of the important features in Kafka is that it's not just a messaging system. It's not just a system for transferring data from one application to another. It also has the capability of storing data and keeping data for as long as you like, so that applications can consume that data at any time, or even the same application can consume that data multiple times if desired. So Kafka supports a couple of different data retention strategies that you can utilize. The most common and default strategy is what we call the delete retention policy, which is typically based on time. It can be based on size of the data as well, but time tends to be the most common configuration for this type of data retention. And the default for this, specified at the cluster level, is 1 week or 7 days of retention. And of course, that's easily configurable in Kafka, and you may very well want to change that. And you can override that setting at the topic level. So maybe different topics have different requirements in terms of retention, and you can configure that individually for each topic that you create. Okay. So of course, this is a business decision and a cost factor to consider in terms of how long you want to keep your data around. You know, what makes sense for your application? Maybe in some use cases, you're using Kafka as a primary data store, and you want a deeper, longer retention, maybe infinite retention for data in that case. And that is an option in Kafka. So in those cases, you might want a very long retention. Or maybe you have use cases where maybe Kafka is being used more for maybe purposes like streaming ETL and primarily for processing data and then transferring that data downstream to another data system, connecting upstream and downstream data systems. And in that case, maybe the retention period set to a shorter period of time in that case. So it really depends on what it is you're trying to do with the data and what your application requirements are in terms of defining data retention. Really, your only limitation from a technical perspective in Kafka is how much storage you have. As long as you have storage, you can keep data as long as you want in Kafka, so easily configurable. And of course, there may be compliance factors as well that might play into this decision, like GDPR, which specifies strict requirements on removing data in certain cases. So those may also factor into your decision making. The other primary type of data retention strategy that Kafka supports is what we call log compaction, or the compact cleanup policy. And the way this type of retention policy works is based on message keys. And the idea is that with a compacted topic, Kafka will keep the most recent message for each key and remove all older messages with that same key. Okay? So in order to configure a topic to be compacted, you must produce messages with keys. In general, keys are optional in messages, but they are not optional when you're storing your data in a compacted topic, because it only makes sense to use compaction when your messages have keys. And of course, keys in Kafka messages don't have to be unique. They frequently are not unique. They typically are used to identify some kind of logical correlation between messages. And then when a compacted topic, you're usually using a key to identify a piece of state that you're updating over time. And that word update that I just mentioned, something we talked about in earlier sessions is the fact that you can't update messages once they've been produced. The messages are immutable, but what you can do is you could publish a new message with the same key as one that came before and interpret the stream in a way where you only consider the latest message for that key and ignore anything older than that. And that's kind of exactly what compaction is doing for you under the covers, is removing the obsolete data, which are older messages with that same key. And you can kind of see the effect of compaction shown here at the bottom of this diagram, where like if you take K1 as a key, we have messages 0, 1, 4, and 9 that have that key, and then after compaction runs, only the message with offset 9 is remaining. So use cases where you want to model mutable state in Kafka, compacted topics are a good choice for that kind of usage pattern. So say, for example, you want to store user profile information for your application in a Kafka topic, and users have the ability to create a profile, update their profile, delete their profile. A compacted topic would be a good way of storing those changes and only keeping the latest state for that user's profile. So in that case, the key of the message would be the user ID, perhaps, and then all the changes that happen to the user profile would be different messages with that same key, and compaction will take care of removing the obsolete data behind the scenes. So again, a compacted topic is basically giving you a representation of current state for data based on key, whereas a topic with delete retention policy is storing the whole history of changes, all the events that occurred back to a certain point in time. So it really just depends on what it is you need in your application and how you plan to work with the data to determine kind of what sort of data retention policy is most appropriate. But you have those two options, and you can also combine those two options together to give you kind of a third option, which is the combination of delete and compact as well. Okay. By the way, the consumer offsets topic that's used to store consumer offsets internally for consumer groups is also another example of a topic that uses this log compaction type retention policy, because that's a continuous stream of updates that are occurring to consumer offsets as you process data. All right, so now let's kind of take a little bit of a deeper look at kind of how the Kafka producer works internally. So as I mentioned earlier in this session, a lot of the heavy lifting of integrating with the Kafka cluster and actually providing the functionality of the producer is kind of baked into the client library itself, something you don't have to implement directly in your code, which is great. But it is helpful to understand what's happening under the covers so that you can properly configure your applications to take advantage of that functionality. Okay, so in this example on the left-hand side, this diagram, we have an example of our producer record that we create in our application that is an encapsulation of a single message that we want to send to Kafka. And some of the properties of producer record are required, which are kind of shown in orange, and some are optional, which are shown in kind of a lighter gray that you see there. So you at minimum specify a topic and a value. You could also specify key and timestamp and headers and some other metadata associated with that producer record. Then you call send in your application, and that kind of sends things into the producer client library, which is kind of shown in that big light gray shaded box in the middle of this diagram here. And that's all internal to the framework, everything you see in that part of the diagram. So let's kind of walk through that briefly right here. So when we call send, the first thing that happens is that the producer client library will serialize your key and value and headers into bytes. So Kafka does not store data with a high-level data format, data structure. Kafka stores data as kind of raw binary data or as just an array of bytes with no type information or structure or anything like that enforced. So Kafka kind of stores data at a very low level of abstraction, which is nice in that Kafka can store pretty much any kind of data that you want. And the interpretation of that data, applying a specific structure to that data, converting it into a higher level object to work with in your applications is the responsibility of your clients, your producers, and your consumers to do that. So the serializer takes care of converting your data into bytes under the covers to be sent to Kafka and stored by Kafka. And when a consumer receives data, it will receive bytes and it will execute a deserializer to convert that data back into higher level objects and apply any kind of structure to the data at that point. So Kafka itself doesn't really know anything about your message payload. To Kafka, it just appears an opaque set of binary data. Okay. Next step is that we execute a partitioning function against your message to determine which topic partition that message should be sent to. In our last session, we talked about how partitioning can be done either based on the key of the message using a hash-based partitioning formula or round-robin partitioning when your messages don't have keys. So those are the built-in default partitioning functions that the producer supports. And as we talked about, you can also implement a custom partitioning function and register it with the producer as well if you prefer to use your own strategy for partitioning. But ultimately, the goal of that function is to identify which topic partition that message should be sent to. And then the next step is that we buffer the message locally within the producer client, and from that point internally the producer will decide when to send that message out to the Kafka broker and then receive the appropriate acknowledgement. And the when is defined based on some configuration that you define for your producer that defines a level of batching that you might want to do. So this is a way to performance tune your producers is by configuring a certain amount of batching to occur. If you want low latency in your producer, then you might configure batches to be very small or maybe as small as one record per batch, in which case the batches may only consist of a single record being sent out. Or if you want to tune more for high throughput, you might configure the batches to be larger. So these buffers are kind of a temporary holding area for messages before they get sent out to the broker, where we can apply those kind of batching semantics based on what you've configured. And we have a different buffer for each partition because different partitions may need to be sent to different brokers. Partitions are spread out across different brokers in the cluster, so we maintain a buffer and perform batching at the partition level. There's other performance tuning you can do through configuration in the producer, such as compressing messages as well. And so these all kind of, this functionality that we're talking about here, performance tuning the producer through batching or not batching, tuning for low latency or high throughput, enabling compression, customizing partitioning or serializers. All of that's defined through configuration properties in your client code, not specific Java code or C# code that you have to write yourself. It's all done through configuration because it's all implemented internally as part of the producer client library. And once the message lands in this partition buffer on the client side, at that point the send call returns. So that send call is essentially asynchronous in that it does not wait until the message has actually completed the round trip to the Kafka broker before returning. It returns as soon as the message has been buffered locally. So as soon as it's been serialized, partitioned, and buffered locally, the send call returns. And then separately, the acknowledgement will come back from the Kafka broker once the data is actually sent in the appropriate batch to the Kafka broker. The acknowledgement will come back separately. And if it's success, then you will get a callback indicating record metadata associated with that successful response. Otherwise, if there was a failure of any kind, the producer client library can be configured to automatically retry on failure to resend that batch however many times you want until it succeeds. And so that retry logic can all be done internally within the framework and completely transparently to your application. So going back to our earlier fault tolerance example, if a broker fails, the producer will fail, but in most cases, that failure will never be visible to the client application because the producer client library will catch those exceptions and retry internally and will eventually succeed before you ever realize there was an issue. However, if you retry a configured number of times and you still are unsuccessful in delivering the data to the broker, then at some point you will eventually get an exception. So you can configure how long you want to retry within the producer client before actually returning an exception to the application, at which point you decide what to do. So there's a lot happening here under the covers, and again, that's all framework level code, and you have the ability to influence that behavior through configuration properties. All right, so one of the key configuration properties on the producer is to specify the criteria for when a request is complete. And this is a property called AX, and there's three possible values, 0, 1, and all, or -1. And just kind of looking at the examples here, basically what you're tuning with this property is the relationship between performance and durability in your producer. So thinking about what it is you really want to emphasize in a particular producer would help to influence what you set for the configuration of this particular property. So in the first example, AX = 0 is basically fire and forget. So the producer sends the message and never receives an acknowledgement. So we don't really know whether the messages we're sending are actually being successfully received and stored by the broker. Under normal operations, any message you send will be successfully stored, but it's when things are not healthy, when things are going wrong, when things are failing, where data loss could be more of a possibility with something like AX = 0. So that's something you have to be prepared for with AX = 0, is that the possibility of data loss because you're not waiting for any kind of acknowledgement. The benefit with AX = 0 is high throughput, high performance. Right? So AX = 0 gives you the highest performance but the lowest durability. AX = 1 is the default setting for this property, and it's kind of a balance between performance and durability in that it does wait for an acknowledgement, but only from the leader for the given partition that you're writing to. It does not wait for all the replication to complete, but only for the leader. So here you have a much higher probability that the data is safely stored in Kafka and an acknowledgement of that fact, but data loss could still occur in very unlikely scenarios. But of course, in some cases, even if it's very unlikely, you don't want to take that risk, right? So x equals 1 is kind of a balanced configuration between performance and durability. And then finally, x equals all, or minus 1, is where the producer will actually wait for the message to be committed in the Kafka cluster, which means received by the leader and all the in-sync replicas for that particular partition before returning acknowledgement. So here we have to wait a little bit longer for the acknowledgement, but we have a much stronger durability guarantee. So x equals 1 gives us, x equals all, x equals all gives us the highest level of durability, but the lowest level of throughput. Of course, this is all relative. Kafka is a very high performance, high throughput system. Compared to other messaging technologies, no matter which one of these options you choose, but x equals all will definitely have lower throughput and performance than something like x equals 0 or x equals 1. So this is up to you to decide, and you can configure this on a per producer basis. Maybe for some use cases, a little bit of data loss is acceptable. For other use cases, it's completely unacceptable, and you can configure each producer accordingly. And then a little bit more on delivery guarantees. There's kind of 3 different delivery guarantees that Kafka can support for your data, and processing guarantees as well on the consumer side. There's at most once, at least once, and exactly once. So with at most once, this would map fairly closely to x equals 0 that we just talked about. So with at most once, data could be lost, but you don't duplicate any messages. So x equals 0 pretty much gives you an at most once guarantee. At least once is where we don't lose any data, but in certain rare cases, we could introduce duplicates. And so this could happen with x equals all, for example, in certain rare cases. And we'll kind of look at an example of this coming up on the next slide. And then we have exactly once, which is kind of the best of all worlds, where every message is sent, every message is received and stored, no data loss, no duplication, right? So that sounds like the ultimate option right there. And historically, Kafka did not provide an out-of-the-box exactly once guarantee, but that has changed now. And Kafka does actually provide an exactly once semantics that you can utilize. So as of more recent versions of Kafka, you have all 3 of these options that you can utilize. So to kind of talk about that exactly once semantics in a little bit more detail, because I think it's important to understand a little bit more about what benefits that provides and how that works. The first step down that road is what we call idempotent message production. So in other words, we want to prevent duplicate messages from occurring. which is what we get with at least once semantics. So that's kind of illustrated in this diagram here on this slide. So at the top, we see the kind of the normal happy path scenario where a producer sends a message to the broker appends that message to its local log and returns a successful acknowledgement. All good. Every message is produced and received and stored, no data loss, no duplication, everything's great, right? The issue where duplication can occur happens when there's some kind of failure in this pipeline. So in the example at the bottom of the slide, we have a case where we're sending a message to the broker appends that message successfully to its local log and then replicates that message to its in-sync replicas. But then for some reason, the acknowledgement's lost, right? Something happens there, we lost the network connection, the broker went down, whatever the case may be, and we never got the acknowledgement back on the producer. So a producer configured with AX equals all has no choice but to assume that that message was not successful, and what it's going to do is it's going to resend that message. And that typically happens automatically as part of the automatic retry mechanism that we just talked about. And in this case, that would end up introducing a duplicate message. So we didn't lose any data in this case, but we ended up introducing a duplicate message because the producer lost an acknowledgement along the way. So the idempotent producer is a new feature that was implemented as part of the exactly once semantics support in Kafka. And by the way, that was Kafka 0.11, where all of this new exactly once support was first added, which is actually now a couple of years old, so not that new anymore. It's been around for quite a while now. So with a single configuration property, you can now enable idempotent message production, which will ensure that as long as the producer is running, that when it's sending data to a particular partition, there will be no duplication of data. So if there's like a lost acknowledgement, like you see in here at the bottom of the slide, we would not produce a duplicate message when we resend. And the way that works is we attach a sequence number to every message that we send to the broker, and the broker will compare that to what's already stored. Says, oh, I've already seen this message with this sequence number before. It won't create the duplicate on that side. So this is kind of one of the foundational parts of the exactly once semantics implementation in Apache Kafka. And you can enable this very simply with a single configuration property on the producer. But actually, to take advantage of the full capabilities of exactly once semantics, it involves utilizing additional functionality, which we call transactions. And if we've worked with databases before, and I'm sure all of us on the call have at one point or another, we're probably all very familiar with transactions from a database context. Well, the transactional API in Kafka looks very similar, where you can start a transaction, send a bunch of messages, potentially different topics, different partitions, and then have all of those messages across all the topic partitions committed as an atomic unit with an exactly once semantic guarantee. So this kind of extends the model of the idempotent producer across multiple partitions, across more failure scenarios, and extends this across to the consumer side as well. So use cases for exactly once semantics are cases where you're very sensitive to message duplication, like tracking ad views or processing financial transactions, where duplication can be very problematic in terms of the effect on your business, or stream processing, where maybe you're computing an aggregation like a sum or an average, and processing an event multiple times could end up resulting in an incorrect aggregate result. And if you need accuracy in your Aggregations, exactly one semantics can help prevent that duplication. And again, this can tie into the consumer side as well, where consumers can be configured to only consume messages that are in committed transactions, that do not see any messages that are in flight within a transaction or are in aborted or rolled back transactions. And you can build applications, for example, that consume from a topic, process the data, and write results to another topic. We call this the consume, process, produce pattern, which is very common in Kafka, with an end-to-end transactional guarantee, where, for example, the consumer offset of the message that you're processing doesn't get updated until the results of that message processing are produced. And those two operations, updating the consumer offset and storing the results of your message process, both happen in the same transaction atomically. So it's a really powerful feature. Not necessarily for every use case needs it, but there are definitely many use cases that can benefit from this capability. And this again gives you framework level support for this exactly once functionality. Okay, so a little bit on partitioning strategies now. So we talked about replication quite a bit earlier in this session. Partitioning is the other kind of key functionality in Kafka. Then partitioning gives us scalability for our data in our Kafka topics by allowing us to distribute our data across multiple brokers in different partitions. And in our previous session, we talked about different approaches for partitioning by key, using a hash-based formula. That's what we call semantic partitioning, because the hash-based, key-based partitioning strategy will ensure that all messages with the same key go to the same partition, which can be very helpful in terms of processing the data in a parallel way downstream. Or you can utilize round-robin partitioning when your messages don't have keys to kind of have more of just kind of an evenly distributed, more randomized distribution of data across the different partitions that make up your topic. So you can also implement custom strategies. One thing to mention about hash partitioning is when you're partitioning by key, there's no guarantee that the messages will be distributed equally across the different partitions. For example, if your incoming data, if 90% of your data has the same key, then with hash partitioning, one partition is going to end up being much, much larger than all the other ones. And we call that data skew, and data skews happen sometimes just due to the natural distribution of data that you're working with. So there are some cases where maybe implementing a custom partitioning strategy might be beneficial. Maybe not a common thing to do, but there are certainly cases where that might be useful to have that extensibility. So it's quite easy to implement a custom partitioner and then register it as part of your producer configuration. So when you're implementing a partitioning strategy, some of the things to think about are, what are you going to need to do with your data downstream? You know, obviously one of the key considerations is kind of load balancing or distributing your data, but you also want to think about how that data is going to be utilized and processed downstream. Maybe you need to aggregate the data or join by some key. So maybe you need to ensure that certain logical groupings of data are stored together in a partition so that you can process those groups of data in parallel downstream. Or maybe you need an ordering guarantee for a certain subset of messages. And that's a very important point, that one right there. Because in Kafka, the ordering guarantee of your messages is at the partition level, not at the topic level. So there's only a guarantee of message ordering at an individual partition level from a single producer. So if there's a specific set of messages that must be processed in a particular order in order to kind of meet the needs of your application, then you want to ensure that they go to the same partition to take advantage of that built-in ordering guarantee that Kafka provides. If they go to different partitions, there's no guarantee that you'll process them downstream in order. So That's one reason to take advantage of semantic partitioning by key or some other custom strategy. And then there could be other reasons as well, like concentrating data for storage efficiency or indexing purposes or something related to the downstream processing that you plan to do on the data. So it's quite common to use some form of semantic partitioning in the data because we have a lot of use cases when working with data in Kafka that require some statefulness. And what we mean by stateful processing is where you need to operate across a group of messages instead of just each message individually. And having that group of logically related messages co-located in the same partition will definitely help in terms of parallelizing that downstream processing. All right, so now let's kind of take a closer look at how consumer groups work in Kafka. And we talked a little bit about this conceptually in our previous session. So a consumer group is a way to scale out our consumption by running multiple consumers and distributing the workload across those multiple consumers for processing our data with hopefully higher throughput as a result. So the way that we distribute work within a consumer group is at the partition level. So to form a consumer group, it's as simple as just specifying a common group ID configuration property. So it's a single configuration property in your consumers that you can use to identify which consumer should be part of the same group. And then all the coordination and the distribution of workload, data balancing, things like that is kind of done for you by Kafka. The combination of the client library, the consumer client library, and the Kafka brokers themselves. So it's a really powerful feature in Kafka for scaling out consumption. And the idea, again, is to allocate a different subset of the data that you need to process to each consumer by partition. So each consumer can be assigned 0 or more partitions for the topic or topics that you've subscribed to. And a partition will only be assigned to one consumer within each group at a time. So that's an important point to mention. So while a consumer can be assigned multiple partitions, if you look at one specific partition, it will only be assigned to one consumer at a time, right? Because we only want our messages to be consumed by one consumer within a group. Because think of a consumer group as being a single application, right? An order validator or a payment processor or a fulfillment system that's processing our orders from our topic, right? All the consumers in that group are performing one function, executing the same code, right? And you can have different consumer groups to represent different applications, but each consumer group logically represents one specific type of application. So we typically want each message to be consumed by only one consumer in that group. So that means that each partition is assigned to only one consumer in the group at any given point in time. And of course, that also helps to ensure that we maintain ordering guarantees that we just talked about as well. So we might have a consumer group that performs order validation and a different consumer group that does payment processing and a different consumer group that does order fulfillment, all processing the same topic. But here we're just looking at one consumer group and the allocation of partitions amongst the consumers in that group. Okay? And how the partitions get assigned to the different consumers in the group is configurable. There's some built-in strategies that you can utilize, and you can customize that as needed. And one important note about consumer groups is not only do they provide scalability for consumption, they also provide automatic load balancing and fault tolerance. So when any changes occur within this consumer group or the topic or topics that you subscribe to, the consumer group will adapt to those changes automatically. And that's a really powerful feature without any manual intervention required. And we kind of see that illustrated right here, where at the top we have a consumer group with two consumers, each assigned two partitions from the subscribed topic. And then we say, well, we need some extra throughput in this consumer group, so I'm going to start up a third consumer with the same group ID, and Kafka will detect that there's a new consumer in this group and will trigger what we call a rebalancing operation, which basically means recomputing the partition assignments and reallocating the partitions amongst the available consumers in the group, so that that consumer C can immediately start providing some benefit to our parallel processing here. So rebalancing is automatically triggered anytime the composition of the consumer group changes. So we see that in these examples in the middle and the bottom of the slide, where consumers added to the group or consumers removed from the group. So those kind of changes are automatically detected, as well as any changes to the topics that you subscribe to. Increase the number of partitions, a change to the subscription, anything that affects the ratio of consumers in the group to partitions in the topic or topics that you've subscribed to will trigger this automatic rebalancing. And the way this works is there's a group coordinator component in the Kafka cluster that is kind of monitoring the state of the consumer group and detecting when any changes occur and triggering this rebalancing operation. And this kind of consumer group coordination protocol that's utilized internally to make all of this work is actually general purpose and is not limited to just consumer groups. In fact, Kafka Streams and KSQL and Kafka Connect all take advantage of this same protocol to provide scalability, fault tolerance, and distributed load balance execution within the client framework. It's a really powerful feature for extending those key benefits of distribution, scalability, fault tolerance to our client applications, right? And allowing our client applications to have those characteristics without having to implement all of that from scratch. Okay, and I know we're getting close to the end of our time here, so last couple of slides in our session. Troubleshooting Kafka. Kafka, being a distributed system, has a lot of components that you may need to monitor and look at for troubleshooting purposes, and there's a lot of options available to you for this purpose. The Confluent Control Center, if you're working with Confluent platform, provides a great tool, a web-based tool for monitoring key metrics in your cluster, and tuning your cluster, configuring, comparing configuration, and a lot of other features as well. So a lot of the key metrics that are available in your Kafka environment are summarized, aggregated, and visualized in the Confluent Control Center. So this is a fantastic tool for helping you troubleshoot and monitor your environment. And you can set up automatic alerts and things like that as well. Log files, we have lots of log files available for additional troubleshooting from all the various components that run in your Kafka environment, provide detailed information about what's happening internally, and there's some special configuration settings that would allow you to do more specialized logging of specific functions, especially around security, like SSL or Kerberos or authorizer type operations. And again, even if you're not using the Confluent platform, there are a tremendous number of metrics that are available for you to access via JMX or other reporting type mechanisms that you can take advantage of from implementing your own monitoring and troubleshooting type solutions. But the Confluent Control Center provides a great out-of-the-box solution for that. And then, of course, for many of us, security is a very important consideration when utilizing